it will not be only an optimal transport talk, as also the title suggests. It will be so optimal transport has been, let's say, a very fashionable topic in the last 40 years now. And I think one of the reasons that it found application to many areas. So yesterday I tried to give a sense of it, but today I will take one topic, which is the question of stability in inequalities, geometric and functional inequalities. And I will show you a situation where optimal transport actually plays a very, very important role. It's really a fantastic tool to study these problems. But there are also situations where just it doesn't work. And I think it's also good to give this message, because sometimes people are like, oh, I try to use optimal transport, it doesn't work, what should I do, what should I do? I say, well, maybe just give up on optimal transport. Sometimes it's also good to, to be honest, right? And move on. So there are some things that you can do and some that you cannot. And I hope to convey a bit of this. So if you want to talk about the topic, I will take it a bit from with a bit of a historical perspective. Yesterday we discussed Monod and Kantorovich. Today I will discuss other people. So we start with Euler. So to talk about calculus variation, there is Euler, who wrote a very influential work in the mid-18th century. And this is his paper, and the title you see in Latin, and is a method for finding curved lines and joint properties of maximum and minimum, or solution of isoperimetric problems in the broadest accepted sense. So Euler was studying already problems of minimizing or maximizing, so finding extrema in a variety of problems. He was interested also in isoperimetric problems. And the kind of question that you could think is like, especially like in the calculus of variation, although I'm not talking yet about calculus of variation, let's say you have, the idea is the following. You have some function z that comes from physical considerations. And let's say you are you have the real axis here, x is one-dimensional variable. Y of x, for instance, could be the height whose graph represents a curve. And what you are trying to do is to find the best possible y that minimizes or maximize, let's say, that integral. And the classical example is the brachistochrona. So let's say you have 2 points A and B in the plane, and you want to find the shape of the curve so that when you take a point of mass and you let it slide along the curve under the influence of gravity, will go from A to B in the shortest possible time. This was a classic problem in the calculus of variation. So that's one of them, and there are many others that were investigated. So Euler wrote this paper, which was very influential, and he treated this by means of geometric considerations. He did many geometric considerations to try to study and find optimizers of these problems. But then, in that case, actually he used a very simple instance of the so-called Lagrange multiplier method that maybe some of you are familiar with, or probably most of you. But it's only a few years later that there was the big revolution, and I'm also, as an Italian, I'm proud because Lagrange is Italian, was Italian, although people think he's French. So Giuseppe Luigi Lagrange, in 1955, when he was only 19 years old, he wrote a letter to Euler, and he explained the technique that he called the technique of variations. And Euler looked at this letter, and he wrote the following: "Ever though the author of this had meditated a long time and revealed to friends his desire, yet the glory of this first discovery was reserved to the very penetrating geometry of Turin Lagrange, who, having used analysis alone, has clearly attained the very same solution which the author had deduced by geometric considerations." So this is the moment where let's say the approach of Euler was combined with the method developed by Lagrange, and now you're familiar with the Euler-Lagrange equations that you compute maybe when you have functionals, and then Euler dropped his method, embraced the one of Lagrange, and renamed the subject calculus of variations. As you can see, there are many spellings, right? Lagrange all together, Lagrange broken, and Lagrange. He signed himself with multiple ways over time. So I'm using all of them without thinking too much. And so he started the calculus of variations. We are at the middle of the 18th century. And since then, well, this has become a very fundamental topic in mathematics. And the goal in the calculus of variations, again, is, as I explained before, you want to find minima or maxima or some functional, some energy. And for this, let's say, presentation, I will discuss two very classical examples. Well, I chose them for, you will see why. And one is the isoperimetric inequality that we already mentioned yesterday briefly, the soap bubbles, the crystals. And then there is a second one, the Brunn-Minkowski inequality, which is something which maybe some people sometimes are less familiar with, but is actually very much connected to isoperimetric inequalities, and is also an important inequality in convex geometry. So I will now take these two inequalities as a way to present both the inequalities, but also the connections to optimal transport. So if you remember yesterday, for those of you who were present, I explained to you that we wanted to understand how, let's say, crystals or soap bubbles change under the influence of external forces. And I told you that, okay, if you want to understand how the shape changes, you can try to use optimal transport. But, I've been very vague there. So now today we try to get a bit more of a sense of what do I mean when I have two shapes and I want to compare with them using optimal transport. So here is, now let me start with setting up the problems, and then optimal transport will come on the way of the discussion. So a basic question in the calculus of variation is, of course, to find or characterize the minimizers. Like in the case of the brachistochrona, you want to find the curve, right? You want to find a formula for the curve that gives you this best shape to minimize the travel time. Fine. But then, if you have found it, you could ask something more. And you could ask yourself, are minimizers stable? What do I mean by that? So suppose that you have a function, a set, it depends what inequality you're looking at, that almost attains equality. Can I say that it's close to the minimizer? So for instance, in the case of brachistochrona would be, suppose that I give you a curve, and they tell you that the time needed for the particle to go from A to B is like very close to the best possible time. Can you prove that then the curve has to be very close to the optimal curve? So the information I give you is just that it's optimal energetically, so it has almost the best time. And from that you want to show that the shape is almost the same. That's the kind of stability result that I'm looking for. And this you can set up for essentially any inequality. You have an inequality, first you find the minimizer, you characterize them, and then you ask yourself, are they stable? In this sense. Okay, so let's start. So the talk will try to discuss this question in two examples, which is about isoperimetric inequalities and Brunn-Minkowskis. So what is the isoperimetric inequality? Maybe I just go to this one. Okay. The isoperimetric inequality, it's yesterday we saw it in the simple case of the two-dimensional plane and three-dimensional situation. So in the plane, you remember the Didot problems, which tells us that among all possible two-dimensional shapes, the best way to enclose a certain amount of area, if you want to minimize the perimeter, is to draw a disk. So there is an inequality valid in every dimension, not only 2 or 3, but n. And the inequality is the following. It tells us that if you give me a set E, a smooth set, like in the picture, with a given volume that I denote by bar E, I mean these two bars, the volume of E, then there is a relation between the perimeter, so the perimeter is the area of the boundary, and the volume. So the perimeter has to always to be at least, so greater or equal than a constant, which is n, the dimensional diameter space. The volume of the unit ball to the 1 over n is just another constant. And then the volume of the set raised to the power n minus 1 over n. So this tells in particular that once you fix the volume, then you have a number on the right, and then the perimeter will always be greater or equal than the number. So it cannot be too small, it's blocked. And this inequality is sharp because there are cases where the equality is attained. So you cannot write anything better. actually we know exactly when it's attained. This is true if and only if E is a ball. Okay? So this is the so-called sharp isoperimetric inequality in the plane. So which tells us that what we said yesterday is correct. So Dido was right. The disk is the best solution in the plane. So bubbles are the best solution in R3 and so on. And this is true in every dimension. Okay, so now the question is, suppose that I don't tell you anymore that I have equality. So what this line tells us is the following, right? So if I have equality in this inequality, then I have to be a ball. And the question you want to ask is, if I have almost equality, is it true that I'm almost a ball? So this was the question of yesterday. I add a bit of energy to the system. In that sense, it's like now the perimeter will not be exactly equal to that. So I need to formalize that. So the way I'm going to formalize it is the following way. So first of all, I have to tell you what does it mean to have almost equality. And I do it with this formula. So I just rewrote the isoperimetric inequality. So the isoperimetric inequality was perimeter greater or equal than what is at the denominator of delta. And another way to write the isoperimetric inequality is to say that delta is greater or equal than 0. I just rearranged the terms. The reason why I like this way of writing more than you could tell me, why don't you write just perimeter minus NB1 volume of E? I could have done that as well. But I don't like that because if you take a set and you shrink it to make smaller, 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 then you see the sides go to 0. So here I also have a trivial equality if I just take a set and instead to shrink both sets. Just I take the set and take it smaller, smaller. The volume will go to 0, the perimeter goes to 0. But I'm not capturing anything in that case. So I want to avoid this scaling trick that you just take a set and you shrink it because it will not give me any information on the shape. While if I write the inequality in this way, by taking the ratio, if you take a set and you dilate it, let's say by factor 2, delta doesn't change. So delta is invariant under dilation of the set. So you cannot scale the volume in this inequality. So the isoperimetric inequality is the first one, delta greater or equal than 0. And the characterization of minimizers is the second line, delta is 0 if and only if E is a ball. Okay, so this is my notion of being almost a minimizer. Delta is small. And now I have to tell you the second part. So my goal is to show that if delta is small, then I'm geometrically close to a ball. What does it mean to be close to a ball? In which sense? The way I'm going to do it is through what we call the symmetry index of a set, which, okay, here is the formula, but you can just see it in this picture. You take your set E, you move it, so, okay, you take your set E, you choose the radius R so that E and the ball of radius R have the same volume, and then what you do is that you look at the center X, the best possible center, so that E and the ball overlap as much as possible. So you look for among all possible balls of radius R, you translate the ball so that you have the maximum overlapping. And then you measure the volume which is not in common. This is E delta BR of X. So this is the volume I'm measuring, and then I just divide by E to make it, again, scale invariant. So I want a quantity that is invariant if I dilate E. So if E is stretched by factor 2, this quantity doesn't change. Okay, so it's just a geometric way to measuring how close I am to a ball. If A is 0, it means that I have a ball which perfectly overlaps with myself, which means I'm a ball myself. Okay, makes sense? Okay, and now the question we have is, now I have a mathematical question because I defined all the objects. Is it true that if delta is small, the symmetry is small? That's what I want to study. Actually, I would like to do even better. Can I find something more explicit? Can we find positive constant, C, possibly depending on the dimension, and alpha, possibly depending on the dimension, such that the asymmetry is controlled by the deficit to a power? So this would be like a stronger statement, right? I'm not just telling you that if one is small, the other is small, but I'm giving you really a quantitative way to tell you how the two things are related. Okay? So you could ask yourself, what about this exponent? So you can try so when you have an inequality you want to prove, you try to first to start with examples. And the first example you can try to understand for this inequality is when you look at an ellipsoid, because it's just a perturbation of the ball. So you start with a ball of radius 1, and then you perturb the axis. Let's say one axis you dilate by 1 plus epsilon, the other one you shrink it by 1 over 1 plus epsilon. The volume doesn't change. And then you compute explicitly what is the symmetry and the deficit in this case. Okay, so you just take the ball of radius 1, you put it on top, you compute the asymmetry, and then you check the perimeter of this, and you see how it goes. This is a computation, you can do it. There is a Taylor expansion. So the asymmetry goes like epsilon, delta goes like epsilon square. Okay? Now, once you know this, you say, okay, let me take these quantities and let me plug them on the top, because that's the inequality I want to be true. And then once you test that inequality on this example, you immediately discover that alpha cannot be larger than 1/2. Otherwise, the inequality is false. So I'm trying to prove an inequality which is true. So better be true at least on ellipsoids. And this is only possible if if alpha doesn't pass 1/2. And this 1/2, this example, you can do it in every dimension. You can take an ellipsoid in a Rn, you shrink one, you dilate one of the axes, you shrink another one, you just do the same computation. And then you can keep the other n-2 if you want fixed. It doesn't matter. You will see the same behaviors. Okay, so we have an inequality, we have an upper bound on alpha. What can we do? Well, the idea is to get a theorem. And the theorem is, yes, the inequality is true. It's true with alpha equal 1/2 in every dimension. So this is a theorem that was first proved in every dimension by Fusco-Maggi and Pratelli in 2008. Then we gave a different proof with Maggi and Pratelli in 2010, and I will explain this in a moment. This is the proof via optimal transport, which is also connected to crystals. We'll discuss this. And then Ciccarese and Lunardi showed that there is a third different approach for the same inequality. So now we have 3 different proofs of the same result. Okay, so let's try to get to this. So if you want to prove an inequality like this, A controlled by deficit, what do you need to do first? You see, this inequality, this stability inequality, in particular implies the supermetric inequality. It tells you that delta is non-negative. This is stronger than the supermetric inequality. The supermetric inequality is delta non-negative. This is delta greater than something positive. So if you want to prove a stability result, at least you need to be able to prove the inequality itself. So that's a general principle, right? You try to improve some result, first make sure you know how to prove the easy version. So maybe some of you know a proof of the supermetric inequality. Maybe some know the one by optimal transport, some will know other approaches, standard symmetrization, whatever. There are many proofs of the supermetric inequality by now. And I want to present it one to you, via optimal transport. Which will explain again what we discussed yesterday. So this proof, so I will comment on this now. I wrote a name on top, Knotes-Gromov's proof of the supermetric inequality. So the first proof of the supermetric inequality using transport theory, not optimal transport because it didn't exist yet, is due to Knote. This morning we had also a talk on the Knote maps. So one could use this map, the so-called Knote map, to prove this result. This is actually what Knote did in the 50s. Just this proof was kind of forgotten, I would say, by the community. And then, especially by the convex geometry community. In fact, in the early 80s, Gromov, together with Vitaly Milman, found the same proof again. And only later they discovered that Knote had already done it. And then what happened is that once they knew that Knote had done it, they didn't publish it because they say, okay, it's already known. But since they felt that it was a bit lost in the literature, there was a Willman that was editing a volume on in convex geometry, and then he asked Gromov to write just the proof as an appendix in the book. And so that was written, but then over time, people start to refer to it as the Gromov proof. And Knote was forgotten again. So if you hear, Gromov proof has inequality. And to be honest, it was really Knote. So I cite both just because that's the way it's known, but that should be the right credit. It's really to Knote. And both proofs also, the Gromov was still before the Brenier theorem. So it was before optimal transfer. So what is this? Let's try to set up the notation. So the idea is the following. I have a set E, which is my competitor. It's a set for which I want to prove the isoperimetric inequality. And I have my candidate optimizer, B1. I still don't know that it's the optimizer, but I believe it to be the optimizer. Okay? So, for whatever reason. And then the idea is that I want to deform this set into this set. How can I do it? Well, you could try to find a nice map. So there are many maps that deform a set into a set. Or you could think differently with an optimal transport mindset and say, okay, let me associate to a set a probability distribution. How do I do? I just take E and then look at a constant density inside E. So I take the indicator function of E normalized by its volume. This is like a constant density inside the set E. And then I do the same in B1. And I call this density G. So these are just two constant densities inside the two domains. These are now two functions, f and g, that have integral 1, both of them. And now there is a French mathematician, Brunn-Minkowski, that tells me that I can do something once I have two probability distributions. I can send one to the other. And not only I can do it with the gradient of a convex function. So this is the optimal transport theorem that you can take just as a black box. You don't even need to know what is optimal transport at this level. That's also, I think, also the beauty of it. You could just ignore what it is. There is no optimality, there is no cost, there is nothing here, there is no optimal transport. It's just someone tells me that if I have two probability distributions, there exists a function phi in a Rn convex whose gradient, grad phi, transcends f to g. So it moves them. You have to think that now f is like a constant distribution. So it's like if I had a bunch of sand, which has the shape of an E, and then I transport the sand so that this sand now takes the shape of a ball, of a disk in the play, right? If I was just playing with the sand on the beach. Okay, so this is my black box, and I'm going to use it in some way. How I'm going to use it? So I have this map that takes points in E and maps to points in B1. What property can I extract from this? Well, there are three properties that can I extract. First property, 1, the modulus of T is less or equal than 1. That's the easy one, because if I take a point in E, its image will be in the unit ball by construction. And then the unit ball, by definition, are the points which have modulus less than 1. That's how you define the unit ball. All the points that have norm less than 1. So 1, it's easy. Second one, if I take the transport map, I take the gradient. It's a matrix. And I take the determinant of this matrix. This determinant is constant, and is the ratio of the two volumes. Okay, here you need to remember your analysis 2 class, which is, or let's say, multidimensional calculus, depends on which country you come from, how you call it, which tells you that if you have a map from a Rn to a Rn, the way volume changes is through the determinant of the gradient. It's the Jacobian determinant. And the point here is that because you are taking a density which is constant and you are mapping to a density which is constant, it means that locally you're not, so you can deform volumes, but constant at each point. So the way you deform infinitesimally the volumes is constant. That's exactly the concept of transporting. You are transporting something constant with something constant, so the determinant has to be constant. And what is the number is something that depends on the volumes. So it doesn't matter now what it, I mean, that's the correct number, but it's just the definition of transport, in fact. Right? You're not concentrating. You're not allowed to take your bunch of sand and makes it more concentrated in some region and less in another, right? You are trying to, by definition, it has to be constant in both domains. So the determinant is constant. So, and then there is a third property that I will discuss in the next slide that relates the divergence of my transport map to the determinant of the gradient. And now let's just believe 3 for a moment. So if you believe, well, okay, first property, I hope I convince you. Second property, I hope I convince you. Third property, just now you need to believe for the moment. And now we start. What is the perimeter of a set? By definition, it's the area of the boundary. So it's like you take the integral of the boundary of the function 1. Now, where is 1 in my inequality? On the top. 1 is greater or equal than the modulus of t. Let's apply it. So I put a modulus of t. Now, t is a vector in a REM. So its modulus is for sure is greater or equal than the scalar product between itself and a vector of modulus 1s. Okay, so if I scatter the product with something of modulus 1, I will get something less or equal. And what do I have of modulus 1? I have the normal. So I can say that this is greater or equal than t taught the normal to the set, the outer normal. And then there I recognize the flux of the vector field that by the Stokes theorem is the integral of the divergence. Okay? And now once you are there, you see the divergence, you say, oh, property 3, divergence greater or equal. Fantastic. And now I'm here, but I have property 2, the determinant is constant, is that number. Let's plug it in. Done. Okay? So this is a very short and elegant proof of the isoperimetric inequality, where you just combine these 3 informations together. So this proof works with this map, this gradient of a convex function, this Brunn map, as we call it. It works if you apply the Knote map as well. It satisfies 1, 2, and 3. These are the 3 key information. Of course, I didn't explain to you why 3 is true, and in fact 3 is the one where I'm going to use that t is the gradient of a convex function. So for property 1 and property 2, I didn't use anything, essentially. I just used that t was a map that was going to the unit ball, and it was transporting F to G. In 3, I have to use the structure. So let's do it. So since t is the gradient of a convex function, I can compute the Hessian of phi. So phi is a convex function, so its Hessian is a matrix, which is, of course, symmetric, but also its eigenvalues are non-negative. That's the definition of a convex function, if you want. When you differentiate twice, the Hessian is positive definite, or non-negative definite. And now you look at what is the quantity I'm looking at, I want to compute, is the divergence of t. Now, if you substitute for t the gradient of phi, divergence of the gradient is the Laplacian. So the Laplacian of phi, which is, by definition, is the sum of the eigenvalues. But the sum of the eigenvalues, I can write it in this way. N times 1 over n, sum of the eigenvalues. And just, if you simplify the n's, you get the definition of Laplacian. And now, but why do I like it this way? Because this 1 over n, sum of the eigenvalues, is an average. It's the so-called arithmetic mean of the numbers. The numbers are non-negative, so the arithmetic mean is greater or equal than the geometric mean, which is the product of the eigenvalues to the 1 over n, but the product of eigenvalues is the determinant. And that's an inequality. So here was crucial the fact that I had the gradient of a convex function. Okay, so so far so good. So here is a very I love this proof. I must say, maybe I'm biased, but I always love this proof. I think it's very elegant, very neat, very mysterious, I would say also. I mean, why it works, I think no one knows, just works beautifully. I mean, I don't have a deep reason why it works. So what is the point? Is that once you have this proof, you can actually try to prove the theorem I stated to you. So the theorem was, let me maybe go back here. The theorem was deficit controls asymmetry. So what is the deficit? The deficit is essentially, it measures the error from this term to this term. So controlling the deficit means that you know how different is the perimeter from the last term. So if you control that, the difference between the two extreme terms, you're going to control in particular all the errors you made in each inequality. So it means that this, so in particular, so let's say, this minus this is bounded by the deficit, this minus this is bounded by the deficit, and then also this minus this is bounded by the deficit. And then you can try to use this information to extract properties of the transform map. The philosophy is the following. I'm going to prove that if deficit is small, the transform map that has to satisfy all these inequality will be close to the identity map. And then if the transform map is close to the identity map, it means that my two sets were very close to each other. That's the idea. The proof is not that trivial. So it takes 30 plus pages. So I'm not going to do it here, but it works. So the strength of this proof is double. So first of all, that's what I mentioned yesterday. It works for crystals. So what I mean is the following. There is a variant of the isoperimetric inequality, which is called Wolff inequality, that you find when instead of minimizing the perimeter, you minimize some integral over the boundary of some function of the normal. So in the case of the perimeter, it corresponds to take f equal 1. Then you have just the perimeter. But if you take a general f, it has to be convex, some function of the normal, then you have an inequality where you see in the right-hand side, you will not have the unit ball anymore. You will have a set kappa. And kappa will be the unit ball for the dual of f. It's like when you do dual in between norms. You give me a norm, you can build a dual norm, and then you take the ball in the dual norm. And this is the so-called Wolff inequality. So if you take f, so f of nu equal the modulus of nu, so the Euclidean norm. The dual of the Euclidean norm is the Euclidean norm itself. You get the perimeter, and here you get the unit ball. But this inequality is true for every s, which is convex. So the Wolff inequality was discovered by Wolff, but it has really been proved only years later. It's a consequence, for instance, of Brunn-Minkowski. But the point of the proof by optimal transport is double. First of all, you could do the same proof as I did for the isoperimetric inequality to prove this inequality. It's the same chain of inequalities. You just need to play a bit with f and f star. But it's really mutatis mutandis. There is nothing deep there. So it's very robust, this optimal transport proof. And then what we did with Maggi and Pratelli in 2010 was to to carefully control each inequality. We proved the stability, which means that the deficit also for the Wolff inequality tells you how far you are from the optimizer. So you could define everything. The deficit will be that minus that, let's say normalized. The asymmetry will be how far I am from a translation of a Wolff shape, so from kappa, and you can reformulate everything. So that's just a detail. I just wanted to mention this because actually a lot of people this morning were telling me, oh yeah, I want to understand better this crystal stuff. And so I thought at least I should say one thing more, what I meant yesterday. This is the stability result I was mentioning yesterday in my talk. I hope now it makes more sense mathematically.
Is f convex or not here?
Yes, f has to be convex. So you always have some kind of inequality, but then you don't have a nice, so since it's only defined on the normal, you can always make it one homogeneous. And then once you extend it one homogeneous, you want that to be convex. And then you define the dual, and the dual of the dual, it's f itself. Yeah. Good. Any questions on this part? Nothing that I particular. Okay. Now, I like to present this also because it came naturally to us. After we did the Isoperimetric inequality, we say, okay, now let's try Brunn-Minkowski, because Brunn-Minkowski is stronger than Isoperimetric inequality. And optimal transport worked so well, let's make it work there as well. Good. Optimism, you need this. So let me present that, but let me present it in a kind of soft way. First of all, let me tell you what is. So Brunn-Minkowski is about addition of sets. It's a very elementary inequality. You don't need any knowledge essentially to just formulate that. It's just you take sets in a Rn, and you start to add points in these sets. But let me start with the case with one set. So you take a number t between 0 and 1. You take a set in a Rn of positive volume, and you define its semi-sum, ta plus 1 minus ta. What is that? Is the family of all points that you can generate by taking this convex combination of points in A and A prime both in A. Okay, so you take any pair of points in A, and you look at the point which is along the segment, connecting them with weight t and 1 minus t. And then you take this point and you add it to your set. So notice that this set that I'm talking about is larger than A itself, because if you're always allowed to take A equal A prime in that choice. So if you take A and A prime to be the same point, then ta plus 1 minus ta, it's A itself. So for sure, all points in A are contained there. Okay. So in particular, you have this inequality, just by inclusion. And then, once we have an inequality, you can ask ourselves, what happens when I have equality? So, I give you a set in a Rn, and I tell you that every time I do this operation, the volume doesn't increase. What can I say about the set itself? So that's the question. What about equality case? So the answer is that equality holds if and only if the set is convex. It's not totally obvious. It's not super complicated, but it's not totally obvious. Because convex means that if you give me 2 points, the segment is contained. Here I'm just telling you every time you give me 2 points, and I do the convex combination with weight t and 1 minus t, the volume doesn't increase. But I'm not saying that it doesn't increase when you take the whole segment. I'm just adding one. So between a pair, I'm just adding 1 point in the middle. Okay, so it's not totally bad. And actually, there is a more precise statement, okay, that is actually A differ from its convex hull by a set of measured 0. So it's really just, okay, this is just more precise, but just think about the first line. That's the message. You have equality if you are convex. And that's the only equality case, up to sets of measured 0. They always run around. Okay. Now, Brunn-Minkowski. Brunn-Minkowski is more general, because it's about taking 2 sets, A and B, now. So what do you do? Now you take 2 sets of volume A and B, and you do the sum with a weight T, A, and 1 minus TB. You build a new set. Now there is no inclusion. And the question is, what can I say about the volume of this set now, given the volume of A and the volume of B? Is there a relation between the volumes? And yes, and this is Brunn-Minkowski. It tells me that the volume of this semi-sum raised to the power 1 over n is controlled by the volume of this set to the 1 over n, and the volume of the other set 1 over n with the right weights, t and 1 minus t. That's what it is, and you can check that it's a perfect equality if you take balls of radius r. So if you take A, a ball of radius r, B, another ball of radius r prime, then this will be like, this goes like r, this is like r prime, and the sum of the two will be a ball of radius tr plus 1 minus tr primes. So everything is consistent. So it's just, you have this power 1 over n because you're trying to capture radius and not volume. So this power is exactly the one that captures the radius of a ball. So that's the inequality. It's Very nice inequality. And when is equality? If and only if A and B are homothetic convex sets. What does it mean? The sets are convex, both of them, if you have equality, and they're homothetic, which means that they are the same up to a translation and a dilation. So Brunn-Minkowski doesn't see the dilations and translations, so maybe let me go back first here. So it could be that I could dilate one of the two, or translate one of the two, and the volume will not be too affected. Well, it depends now on the T. But the philosophy is that if you have equality, so the two sets have to be convex, and essentially they have to be the same set, up to trivial transformation, translation, dilation. Okay, so it's a kind of very strong inequality, it captures a lot. And this is the precise statement. You can find parameters alpha and beta, translations v and w, and one convex set kappa, so that A and B are equal up to sets of measure 0 to alpha k plus v. So you take kappa, you dilate it by alpha, you translate, and you take kappa, you translate by beta, you translate. So essentially up to a translation and a dilation, A and B are equal to kappa, where kappa is convex. Okay, so that's, but just remember the first line, that's the, so homothety and convexity, these are the two things. So it's a, as I say, there's a very nice inequality, it's very powerful actually, and but now you will see that when we go to stability, this will be actually the fact that the equality case is so big, that's actually a problem, right? So in the isoperimetric inequality, you have equality if and only if you have a ball, up to translation dilation. So the minimizer is roughly unique. There is a ball, then the rest is just trivial transformation. Here, all convex sets are minimizers. And space of convex set is big. So things are tricky here. The Brunn-Minkowski inequality has a lot of applications. And for those of you who are not familiar with that, actually Brunn-Minkowski implies isoperimetric, which implies, for instance, Sobolev and Gagliardini. So there is a whole chain of implications. Brunn-Minkowski is here. I will not discuss it here, but there is actually a nice exercise that one could try to do, which is the following. Take this inequality, okay? Take here as B your set E, the one in the isoperimetric inequality. Remember the isoperimetric inequality, perimeter of E greater or equal than a constant volume of E to the m minus 1 over m, okay? Take B equal E, take A equal the ball of radius 1, okay? And try to let T go to 0 in this inequality. You do a Taylor expansion in T of both terms, so you have to see what it is this as T goes to 0, and the first order term here as T goes to 0 will capture the perimeter. It will be exactly the perimeter of at the first order term, you will capture the perimeter of E. And when you do a Taylor expansion at T go to 0, that's how you recover the isoperimetric inequality, the sharp one. So the linearization of this around T equals 0 is the isoperimetric inequality. So this is stronger, it implies it. Okay, it's not an easy exercise, but for those of you who have never seen it, it's worth trying it. And if you don't succeed, I think if you write on Google or anywhere, even ChatGPT, how I prove that, you will find it very, very quickly. And otherwise, send me an email, of course. But I think now there are many tools that this is a standard argument, so it's known. Okay, so it's a nice inequality, it's very powerful. And I want to understand stability. So to frame the stability, let me do some simplifications. So you can, up to some transformations, dilating, rescaling T, so on, you can always assume that the volumes are 1. So you take your set and you rescale them to volume 1. This will affect a bit the T. You have to change T at some moment. So maybe T is not the same T as before, but doesn't matter. T was a parameter, okay? And then you have this inequality, TA plus 1 minus TB. And because I can always reverse the role of A and B, I can even assume that T is at most 1/2, just by symmetry. It's a number between 0 and 1. Let's assume that it's smaller than 1/2, up to reverse the role of T and 1 minus T. Okay, so that's my inequality. And then Brunn-Minkowski is actually much easier to write. It tells me that if you give me two sets of volume 1, then the volume of their semisum is greater or equal than 1. That's totally equivalent. But I don't have any more powers 1 over n floating around, and so on. It's a nice trick to do this, because then I have an inequality which is probably easier to remember. Okay, so this is my inequality. And then what I want to do, I want to prove stability. What does it mean? It means that this quantity, the delta, so this is you see a deficit that depends on A, B, and T. So right, depends on the two sets, but also the parameter T that I put. And I'm going to assume that this quantity is very small, and I ask myself, are A and B the same convex set now after translation? Because now they both have volume 1, so I don't have the dilation anymore. So is it true that after a translation, A and B are the same convex set? Up to errors, of course. Okay. So, so that's the question. Is it true that both A and B are almost, so if the stability is it true that if this is small, A and B are almost convex, and actually they're close to the same convex set? And then can I even have something explicit? So it's a bit as before. One thing is to say, okay, if this is small, then they're close in some qualitative sense, or maybe something quantitative. Do I have powers? Remember, power 1/2. Do I have constant power, something robust? Okay, so this is a question that we start to work on with Maggi and Pratelli. Actually, so the paper with Maggi and Pratelli was published in 2010, but was done actually in 2007. So that, just to put things, then of course, you know, between when you finish and between you publish, there is always a gap, right? So in 2007, this was done, and we're very happy about that, and that's when we started to think about Brunn-Minkowski. I mentioned this for a reason, you will see in a second. And then we wanted to understand this question. Okay, so the stability, this question has two statements in it, because I have two properties. I'm telling you, if delta is small, I would like the sets both to be convex and to be homothetic. So I have to worry about two properties now, that the sets are convex, the sets are homothetic, okay? So convexity, the error in Brunn-Minkowski controls how far A and B are from their convex hull, so how far they are from being convex, each of them. And then homothety, the error in Brunn-Minkowski controls the difference between the two shapes, right? So I hope to do both, right? That's my goal, is to prove that if delta is small, then I can prove both of these statements. Okay, so when you try to do that, and you have no clue how to start, because when we started, remember, we had no clue how to do this, we said, okay, let's simplify our life. How can we simplify our life? Well, maybe what we could try to do is to take, so we want to prove these two conclusions. Let's make one conclusion an assumption and try to prove the other. What do I mean by this? I want to prove convexity, but I don't want to worry about homothety. Let's assume already that A and B are the same set. So I take A equal B. So then they're clearly homothetic because they are the same by definition. And then I try to prove that they're convex. But he is convex because now there is only one set. Vice versa, I want to prove homothety. Let me assume A and B to be convex first. Now it's an assumption. I don't have to prove anything because by assumption I'm going to assume A and B convex. Let me try to prove that they're homothetic. And then maybe hopefully one day I will even be able to do everything, right? So, you know, you have to start from something. So you start to play with assumptions, right? Okay, we are going to proceed by steps. First, homothety. Assume they're convex. Prove they're almost the same shape. Second, assume they're the same. Prove they're almost convex. And then prove the general case. So, just to be clear, it's not obvious at all that if you do the first two, you know how to do three. But in some sense, if you don't even know how to do 1 and 2, you're never going to be able to do the third one. So at least it's a necessary condition to do, right? So just take it in this way. Okay, so the homothety one. The homothety one is the one that we did first. It was right after we did the Isoperimetric. We say, okay, let's try. Let's assume the sets are convex, and let's prove the stability. Let's try with optimal transport. So first of all, you have to decide what does it mean that the two sets are similar, and then you just define it's very similar to the symmetry. You take a set, you translate the other, you try to overlap them as much as possible, and you compute the volume. That's my distance between my two sets. Okay, they are close up to translation. And now my goal is to prove that if delta is small, this distance is small. That's the homothety statement, the homothety statement. And then the theorem is the following. Let t be a number between 0 and 1/2, then the deficit to the power 1/2 controls D. So it looks like the same as more or less the same as in the isoperimetric inequality. Deficit to the power 1/2 controls the asymmetry between the two sets. This makes sense? So we got the same statement. It's not surprise. How the proof goes? Well, it's the dependence, everything is optimal here. So this is optimal, the T1/2, this is optimal, the 1/2. Cn is explicit. The proof is actually, was published in 2009 and is by optimal transport. You transport, in this case, A to B, and you try to play with the same machinery. So it's not surprising we succeeded because in some sense we actually developed all the tools in the isoperimetric case. And then here it was like, it came out rather easy, I should say. So, okay, good, we did one step. Okay? Then we said, okay, now let's try the other one. The other one is the convexity issue, which is let's take now the two sets to be equal and try to prove that they are convex. So this works. Okay, one thing that I should mention is that when you do the proof, you see immediately the proof volatile transport breaks down completely if the sets are not convex. So you really need something different to do. And you need a new strategy. So let me try to explain to you the homothety issue in a very simple case. One dimension. Usually every one-dimensional problem, you always feel that it should be trivial. And that's actually how we thought we felt. So I can tell you I remember very well that at the beginning we tried to do it directly in n-dimension. And after a while we were getting a bit lost even how to start. Then we said, okay, just to feel better, let's do the one-dimensional case. We're getting too depressed by not advancing in any way. So let's try to feel better. Let's do the easy case. And unfortunately, it didn't work out. In a sense, it didn't feel as better because we were stuck in the 1D case at the beginning. We were like, wait, it's not that easy. It doesn't look like it's such a trivial thing to do. Maybe we were also taking it from the world perspective, but we kind of didn't see the right approach to do it. And then I can just mention this. So let me try just to explain something. So we weren't even sure what was the statement at the beginning. So consider the following situation. Let's take n equal 1, t equal 1/2. So what is the deficit? If you take, so here now we are on the real line. We took a set of volume 1, and we define delta 1/2, which is the volume of the semi-sum minus 1. Okay, so the goal is to prove that if this is small, the set should be convex, or almost. So, question. This is the question we want to answer. Can we prove that this controls this? You think a bit, and then you come up with this example. So A could be the union of two intervals on the real line, which are very far apart. So A is the set on the first row. The semi-sum between A and itself will have all the points in the two intervals plus a third mid-interval. That is what you obtain when you take convex combination of points, one here and one there. Right? So if you take A and the prime in this interval, you will get this interval. If you take A and the prime in this interval, you will get this one. But if you take A here and the prime there, you get this one. So you add a third interval. And this set, so the deficit here is 1/2, because it's 3/2 minus 1. Each interval is length 1/2. But the convex hull is huge. Right? This set is nothing but complex. It's super far from a complex set. It's two intervals which are super far away. So that was a bit depressing because we're like, okay, what can we even prove? And when we were working on it, so we were trying to do this. This was in 2008. Now the story makes sense because I told you 2007 we finished, we had done the other. It was 2008. There was a program in optimal transport. I was here at the IPAM. And then we were discussing optimal transport, many things. But then one day, I don't even remember how it happened, exactly, but by chance I was talking to Terry. And I mentioned this problem to him. I'm saying, yeah, we're thinking about, I'm working on Isoperimetric inequalities, blah, 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 we prove stability. I mentioned what we have done. I say, no, we're trying to think about this, Brunn-Minkowski more in general, about addition of sets to itself, and like the stability of this statement. And then I just mentioned that. He looks at me and say, oh, and that's known, it's Feynman theorem. And I say, what is Feynman theorem? And just to say, yeah, it's here in my book on additive combinatorics. I say, oh, good.
Yeah.
So he gave me the reference. Thank you, Terry. And I looked at it, and it was a statement about arithmetic progressions, which at the beginning looked very different, but then you think a bit, and then in fact it all makes sense. It's a statement about arithmetic progression in Z, but if you discretize R and you think made of very short intervals, and you approximate with Z, and you take the statement, you pass it to the limit, you just get what I was looking for. So in fact, Feynman's, when you take Feynman theorem, you just specialize it to R, it's a consequence of it, then you get this statement. Take a set in R, volume 1, and assume the density is strictly less than 1/2. So that my counterexample doesn't work. This union of two intervals is not admissible. If you assume this inequality, then you have this beautiful stability result that tells you that A is close to x convex L, and the volume of the difference is bounded by 2 times the deficit. So constant is very explicit, power is 1, perfect state. Okay, so that was encouraging. We had the 1D case. And then the question was, what can we do in higher dimension? Unfortunately, okay. Then there is no good Feynman for this problem. So there are results in higher dimension, a la Feynman, but they will not give us what we were looking for. So, as I say, Feynman's theorem is actually about the structure of additive subset in Z. And actually, it also works when you have T different from 1/2 and A different from B. So, truth is, if you look at stability of Brunn-Minkowski in 1D, it's a consequence of well-known theorems in additive combinatorics. So that 1D case is covered. Both for A different from B, it's fine. The problem is to go to higher dimensions. So just to make sure, I'm going to close very soon. I'm almost done. So the case greater than 1 was the goal, right? So let me just explain to you first when A is equal to B. Now you have a set in Rn, volume 1. You look at the error in Brunn-Minkowski, which is just the semi-sum now. And then the question is, can I prove that if delta is small, that set is almost convex? And so the first theorem in this direction was due to Mike Christ, who proved a qualitative result. He proved that if delta goes to 0, then this goes to 0. So there is no quantitative, there is no power, there is no estimate, but he could prove already this statement, which is non-trivial, because, as I told you, the space of convex set is a very large set. That was the first statement. And then there had been work first by myself and Jerison, and then the final theorem in this direction is due to Van Intum, Spink, and Tiba. And they proved the following. If delta is small enough, you always need that, then A is close to convex L with a constant, t to the minus 1, delta t to the power 1. So there is a stability result, which is totally sharp. This is the best result you can prove. And in this case, the stability is true with power 1, not 1 else. Okay? And let's see. Yes, all it's optimal. So this closed after, you see, a few years. We are at 2022 when they did that. I mean, this was published in 2022. They did it around 2019. So after 10 years roughly after our theorem, they could do the case A equal B. And then finally, we looked at the general case. And the final theorem is due to myself, Vanito Mentiba from last year. And what we proved is the general statement that if delta is small enough, then A and B are close to the same convex set. And the bound is, again, delta to the 1/2, t to the minus 1/2, which is the same as in the convex case. So this is the, maybe let me just skip the next comment. So this closes at least the Brunn-Minkowski stability. And maybe what I want to emphasize here in the next 90 seconds is the following. So optimal transport, so tomorrow I will give a third talk, and it will be more about optimal transport, how you can use it to prove inequalities, the regularity, how it plays a role, and so on. But the message here is that optimal transport has been fashionable as a tool to prove stability. There are many other inequalities that have been proved and of which the stability has been proved using optimal transport. But I say sometimes you just have to accept that optimal transport is not the tool, and that's a fact. So here the stability is based on many different techniques that have been combined in different situations. So for instance, the Isoperimetric inequality and Brunn-Minkowski for convex set is based on optimal transport. Brunn-Minkowski for n equal 1 is based on additive combinatorics, and then the general case of Brunn-Minkowski is based on many other techniques. And then just to put things in a broader perspective for those of you who are maybe interested in it, there is actually a very nice question that you could ask next again. So just to close up about this whole theory. So here I'm discussing stability of minimizers, okay? So I told you I have some object, a function, a set that almost satisfies the inequality. So it almost minimizes the inequality. So the deficit is small. And then from that, I want to prove that it's close to be a minimizer. And then you could ask yourself, since Euler and Lagrange were so important, what about critical points? So what does it mean this? It means I give you a function which is not a minimizer and is not almost a minimizer, but is almost a critical point, which means that almost satisfies the Euler-Lagrange equations. So every minimizer solves the Euler-Lagrange equation, but it's not true that every solution of the Euler-Lagrange equation is a minimizer. And then you can try to understand whether being almost a critical point implies some rigidity result, some stability result. And for instance, a classical example of this is the Alexandrov theorem. So the Alexandrov theorem is the critical point version of the Isoperimetric inequality. So every solution to the Isoperimetric problem has constant mean curvature, and then you can try to go backward. And the Alexandrov theorem tells you that if you have a set bounded smooth with constant mean curvature, then it must be a ball. So if the constant mean curvature is the Euler-Lagrange equation of the perimeter. So if you're a minimizer of the Isoperimetric equality, you will have a constant mean curvature. And then if you're smooth, you can apply the Alexandrov theorem to know that it must be a ball. Okay? So that's a way to prove that balls are minimizers, the unique minimizers also, if you know that everything is smooth. And then you can ask stability of this statement now, right? I don't have the energy now. The only thing I can play with is the mean curvature. So I could look at this statement and ask myself, give me a set E which is smooth, bounded, and it has almost constant mean curvature. Is it true that E is close to a ball? Does that make sense? So I'm just splitting almost and almost. Almost constant mean curvature implies almost a ball. And the answer is no. You can take two balls and connect them by a small neck. And you can do it so that the mean curvature is actually very close to a constant everywhere. And this is very far from a ball. It's two balls. So this is what we call bubbling phenomenon in geometric analysis. And there are many other examples even for other inequalities. So in general, once you start critical point, you could do this example with many balls. So your set could be a union of 10 balls connected by small necks, for instance. And this would be a connected set which is far from a ball, but you see, it's almost a ball. It's just many balls, one close to each other. It's just that the mean curvature itself cannot recognize one ball from two balls. That's the key point. And this is a very nice direction of research, try to understand the stability of critical points. This is just one example. And for many problems, even for this one, there is still not a conclusive answer. There are theorems, but no sharp result yet, for instance, none in this case. Okay, so I stop here, and I thank you for your attention.